Today we're going to talk about Parikh's theorem. My name is Sooraj Karthik.
I'm Suvan Adhikari.
I'm Kristen Brown.
And I'm Akul Loomba. A little background review. A context-free grammar is defined as a four-tuple, where n is the set of variables, sigma is the set of terminal symbols, r is the set of productions, and s is the start symbol. Here you can see there's an example. A context-free language, CFL, is a language that is produced by a CFG. And then regular languages are accepted by a finite automata, both DFAs and NFAs. Background, Parikh's images. A Parikh image, or a Parikh map, given a finite alphabet, a Parikh image is a function that counts how many of each character there are in W. For example, let sigma be ABC, and let W be AABB, ABAC. This Parikh map would be 431, since W has 4 A's, 3 B's, and 1 C. And then, given a language L over alphabet sigma, we can define this as such, and that's the set of Parikh images over all words in that language. And then letter equivalence. Two words, W1, W2, are letter equivalent if their Parikh images are equal. Similarly, languages L1, L2 are letter equivalent if their Parikh images are equal. So for example, if sigma is ABC, AA, BB, CC, and AB, CC, BA are letter equivalent because both have 3 of each character. And then we can generalize this to say if we have A to the N, B to the N, and you have L2, which is AB to the N, they're letter equivalent because both have exactly N of each character in every word.
So now we can talk about what Parikh's theorem actually is. The theorem states that context-free languages are equal to regular languages if you ignore the order of letters in a word. In other words, any context-free language is letter equivalent to some regular language. An example from before, L1 is A to the N, B to the N, and L2 is AB to the N. These two languages are letter equivalent. And we can show that L1 is context-free and L2 is regular. So this is Parikh's theorem in action. So we're going to sketch a proof by construction for Parikh's theorem that was proposed by German mathematicians in 2011. The general idea is that given a context-free grammar G, we're going to show that we can build an NFA that simulates the changes in Parikh images that happen during a derivation of G. This shows that under the Parikh image, NFAs and CFGs are equally as powerful. So the general idea is that we want to mimic the Parikh images of derivations used by G to generate the language L of G. Before we can do that, we need to define a few more things, the first one being a step. So if we let A to gamma be an arbitrary rule in the CFG, then alpha beta is a step if there exists W1 and W2 such that A is defined and B is alpha and beta are defined as follows. In other words, if there's an alpha where the rule replaces some characters in alpha to obtain beta. And we need one more tool before we can build our NFA, and that's a few projections. The first one is a projection P of n, where P of n removes all of the terminals in W and leaves only the non-terminals, and P of sigma, where P of sigma removes all of the non-terminals and removes all of the non-terminals and leaves only the terminals in W. So now we can finally build this NFA. So we're going to define this NFA for some finite natural number k, and we're going to let the states of the NFA be all vectors in of size n, where n is the size of the number of non-terminals. And we're going to define all of these vectors to where their sum is less than or equal to the finite number k. And we're going to define our transition function, where we're basically transitioning from the Parikh image of the non-terminals in alpha, and our input is going to be the Parikh image of the rule, and we're going to transition to the Parikh images of the non-terminals in beta. And we're going to let our start state be the Parikh image of the start state itself, and we're going to let our accepting states be the Parikh image of epsilon, so it's just going to be a bunch of zeros, right? And the intuition behind this is that we're going to start with just the start states Parikh image, and we're going to apply all of the rules of the context-free grammar, and we're going to accept only those states, only those paths through our NFA that end up with the empty string of non-terminals. So basically our final string is not going to have any non-terminals in it, which is basically how a derivation of a context-free grammar is concluded, right? And so we're going to claim that for every context-free grammar, there's some k where n of k can simulate G. And we can look at the transitions taken by the NFA to see what the Parikh image of each derivation is.
There are a few different applications of Parikh's theorem. One such application is that any context-free language over a unary alphabet is regular. This is because in a unary alphabet, there's only one letter, so the order of characters doesn't matter. A string is uniquely defined by the number of letters there are. Because there is no ordering, and the Parikh images of the two languages are the same, then that means that the languages themselves are equivalent. And we showed that CFLs and regular languages are equivalent if we ignore the order of letters. Therefore, a CFL over a unary alphabet is also regular. Another application of Parikh's theorem is proving that a language is not context-free. To do this, we need some more context. First, a subset is linear if all the elements in S can be generated by a linear combination of a set of fixed vectors, plus the addition of another fixed vector. A subset is semilinear if it's a union of a finite number of linear subsets. Using a corollary of Parikh's theorem, which says that if a language is context-free, then the Parikh image is a semilinear subset, the contrapositive also must be true, which is that the Parikh image, if the Parikh image is not a semilinear set, then the language is not context-free. We can use this information to show that some languages are not context-free if their Parikh images are not semilinear. For example, take the language a to the p, where p is a prime number. Since the Parikh image of this set is the set of prime numbers, we know that this language is not context-free, since the set of prime numbers cannot be represented as a union of finitely many linear sets. This is useful for some languages where using the pumping lemma would be too complex with too many cases, but it would be easy to count the number of each character's occurrence. In these specific cases, Parikh's theorem can be very useful to determining if it is context-free.
So some last applications of this theorem is involving ambiguity. So this proves that a context-free language can have ambiguous grammar, which means that CFGs cannot be converted to an equivalent unambiguous CFG. Ambiguity of a grammar means that the same strings in a language have different parse trees, which has implications for the overhead time for a programming language, because the same program can have multiple equivalent programs that also execute. So the theorem has some implications in the spectrum question. For some background info, spectrum is the set of finite cardinalities in which theta has a model, where theta is a sentence with some first order logic over its vocabulary, which first order logic includes quantifiable variables over non-logical objects, and the cardinalities are just the number of elements in a set. In the 1950s, there were some questions proposed around spectrums. Schultz asked in 1952 what are the spectra of sentences of first order logic. So basically the spectrum of sentences written in the form px, where p is a predicate over the subject x. And in 1955, Astor asked whether the complement of that is also a spectrum of some first order language sentences. And that question is still open. So how does this relate to Parikh's theorem? Basically, Parikh's theorem is used heavily in these questions because for unary models, Parikh's theorem just looks at the spectrum of context-free languages, and Parikh's theorem can also be extended to other relational structures by basically replacing a language with an arbitrary finite relational structures. As long as it's bounded with, it can be replaced. The theorem shows that the spectrum is ultimately periodic as long as the function is a finite successor function, which means it sends a natural number to its next natural number, and theta is MSOL, which means that it's a monadic second order logic, and you can quantify over subsets of elements and relations. Because of these, Parikh's theorem is utilized heavily in that open problem.
Thank you for listening to our talk on Parikh's theorem. We hope you learned something. Thank you.